So let me introduce the next speaker, Christian Wolf, who is a principal scientist in NAVER Lab Europe in Grenoble, while being on leave of a position of associate professor in Salle Lyon. In NAVER, Christian, you are leading the team Spatial AI, with a special interest in embedded computer vision and in machine learning for robotics in general. So with Christian, we will see a lot of robot navigating in a partially known environment. You also have a lot of investment in research network in France, like GDR-ISIS or GDR-AI. Today, you are supposed to discuss how to learn representation to visually guide robot navigating in a 3D environment. So, the floor is yours.
Thank you very much, Nicolas, for this really nice introduction and also for the invitation to the organizers. I'm very happy to be here. So, yes, as I will talk about navigation today, and as Nicolas said, I'm part of NAVER Labs, but actually I recently joined NAVER Labs. I have been an academic for a couple of years at INSA Lyon, associate professor. So the company NAVER I'm working for, you know it perhaps, is global, and they have lots of activities in internet search, online shopping, recommendation systems, NLP, etc. And we at NAVER Labs, the research branch, are focused on ambient intelligence, so technology which is aware of you, yourself, and your surroundings. And in particular, one of the applications we're working on and proud of is navigation. So what you see here is a video, forgot the subtitles because I just cut it together from various sources. So this is the new headquarters from NAVER Labs in Seoul, in Korea, and what you see here is one of, or several of the roughly 100 robots which are already actually navigating there. So this is a production system. NAVER employees can actually right now order coffee or send packets around, so you can with a cell phone ask or request a robot. The robot comes to you, it opens a hatch, you can put something in, and the robot is actually fully autonomous and can deliver parcels, coffee, and whatever you want. So this is done with computer vision, machine learning. The building has been 3D scanned, for example, etc. So what I will talk today is about this kind of navigation ideas and the new research we'll do. So for the moment, the slides I will present today are mostly the work I did before joining NAVER, so which I did with my old PhD group at INSA Lyon. We will work on learning navigation. And so how is navigation being dealt with in the past? Well, basically there are two schools which try to join themselves, classical robotics. And in classical robotics, navigation is heavily based on geometry, maps, localization. So SLAM, for example, the robot actually navigates, builds some kind of 2D or 3D map, and then there are planning algorithms on top of them. Now, all this research has been improved and augmented with machine learning, but still lacks some kind of robustness because, for example, because the situation is not exactly as we try to model it. On the other side of the spectrum, we have machine learning, where basically navigation is trained in large-scale simulation. So here, what you see here is our building in NAVER Labs France, where I work, either seen from the physical robot or in simulation after we 3D scan the building. So we can train robots to navigate, to solve tasks here, and then the problem is how can we make them generalize? So there are also problems, of course. No solution is perfect, and here also we have lack of robustness because typically the simulated situation does not correspond to the real one. So this is the famous sim to real gap, and we need to overcome this. So let's step a little bit back for 1 second, and when we try to find out how can we solve this problem, let's find out what kind of reasoning skills robots actually need to learn. And I tried to come up with 4 of them. So probably the simplest thing which a robot needs to do is obstacle avoidance. So find out what piece on the floor is actually navigable or occupied or in motion. And if it is, stop, go around, etc. So this is related to quite local scene structure. Oh, that was too fast. And if we extend scene structure a little bit further, then navigation also needs to find a local minima, for example. We can't just always follow the Euclidean path to a target. This requires, for example, if I need to exit a room, well, find the exit, find the door. And as in the case here at our robot in Seoul here, well, these robots are actually capable of taking elevators. Well, we need to find the elevator if we need to change the floor. So this is still related to scene structure. A little bit more complex is this carrying affordances. So what does this mean? That means the world around is well, full of people, objects, and some of these objects can actually be interacted with. So for example, here we see that there are keys on the floor of this apartment, and if the robot actually sees them, well, if its current task is to find the keys, well, obviously it should pick them up and get them, but actually it should not even wait for the task to be specified. If it sees the keys, it could actually anticipate, okay, in the past, I have been asked to find these keys, perhaps I should just map them so I can find them quicker next time. And actually we don't want to hard code that, we want actually the robot to discover automatically which actions, which objects are important. And if it's really smart, it actually takes the keys and puts it where they should be, right at the, you know, the thing right beside your door where all your keys are in. And last thing is, well, if we push this a little bit further, then robots should actually be capable of understanding important parts of the world we're living in. So I'll give you one example. So let's say that you are, you want a pillow and you ask the robot to find your pillow. Well, I will not go into details why you should actually, it would be easy to go to the bedroom, but anyway, let's say the robot should find a pillow. So the robot navigates and it finds here, it sees a glimpse of a bedroom here. So you can't imagine that the robot thinks, I need a pillow, there is a bedroom, perhaps I should search there first. So obviously you could hard code that for the specific case of a pillow, but why wouldn't you want to have the robot, why don't you want to have the robot to have a model of the world, tap into some knowledge sources? So for example, tap into language models, and there are recent papers here, for example, in the monologue paper, or the LMNAV paper, which actually try to do that. So they actually use models like GPT-3 or these large language models to actually communicate knowledge to the robot. So this is the goal we have, and we need to do that in large-scale training. And today I will focus a little bit on the types of spatial memory we can put into robots, because robots need to reason, and when they reason, well, they have seen things in the past. They will not try to store everything they have seen, but they will probably learn some representation of the history of observations. And the simplest thing in pure machine learning we can think about is what is called, oh, sorry, I'm still trying to find out what these buttons are. So the simplest baseline we can think about in machine learning, if you want to give a process memory, is the recurrent baseline, where you basically put some Okay, I'm sorry. These buttons seem to be correlated. So you put some recurrent memory like an LSTM or CIIRC into an agent. So the agent here takes a decision on an action to take. So for example, move to a certain direction. He has its old memory, updates its memory, and as an input it gets the current observation. So for example, an image from a sensor. The goal, for example, a goal embedding, what task should I actually solve, and eventually the previous action. So this is the simplest form of memory. We'll come back to it, but we can do better. So what I will talk today here is of 4 forms of memory which are currently discussed in the field of AI for robotics, 2 of which are pretty classical. Metric maps and topological maps have been here for some time in robotics. And they have been what we can call neuralized, so they have been put into neural networks beyond just using these maps as input neural networks. So how does this work? Let's start with, for example, metric maps. So you can start again with this projective neural, with this recurrent baseline, which for the moment only has this vectorial flat representation. And you can give it additional memory. So this is work done by my student Edward Beeching. And you can, for example, say that I'll take the egocentric observation here, calculate features from it, and then I do inverse projection to some latent map. Here, this inverse projection requires camera calibration, camera intrinsics, and depth. You need a depth tensor for that. And then you project actually pixels from here to the latent map, and this projection is still learned. So what actually is put on a specific point on the map is learned. Where it is put is not learned. This follows geometry. So this is one version how to mix geometry and learning. And we showed here in this work that this can be learned by reinforcement learning. And we can even augment this with some form of attention reader where the agent can basically say, I would like to find out what happens here, or I would like to find this and that object. So this combines actually two forms of memory, and this memory also can be seen as a bird's eye view tensor, right? It follows the agent, so as the agent moves, the memory follows it and moves with it, like classical metric maps in robotics. So we have also shown in recent work that this can be combined with self-supervised learning and learning from privileged information in simulation. And together with projective mapping, we obtained first rank in the multi-object navigation challenge last year. So this is work by my student Pierre Marzin. Okay, now the field actually had some interesting development with respect to these maps, because these maps require two things. They require camera intrinsics, which are not complicated to get by, but also depth, right? But depth is either difficult in certain situations or noisy. So recent work, there are a couple of papers here, among which is the ICRA-best paper, this year's ICRA-best paper. It changes a little bit, so they still use camera intrinsics to find the correspondence between image columns in the egocentric image and polar rays in the bird's eye view. But the remaining ambiguity, which requires depth to solve the position on the column versus the position on the polar ray, is then solved through large-scale machine learning from data. So basically you find out how objects look like and where they could be on the polar ray. So next are topological maps, which are also quite used in robotics classically, and they can also be put into neural networks. So topological maps are basically graphs. This is how you determine in the morning how to go to the bakery, right? You don't reconstruct a 3D model from the environment. Probably you see first I need to go to the door, from the door I need to go to etc., etc. So we have worked on that also, where we try to find out how we can make the robot cope with topological maps it produces itself, which are inherently uncertain. So if the robot produces points in space and then links them through connectivity, it thinks, okay, this point here should be connected to this point. It might be wrong, right? So this is all uncertain. And what we did here is we created with various algorithms 75 million of these graphs and then learned how to solve these graphs, including this uncertainty. So we train on multiple instances, and then with the knowledge gained on these instances, how are these uncertainties actually probabilistically distributed, we can better solve a single instance. So I'll give you one example here. In simulation, so the purple points here are actually graph edges, and the robot here plans first on a higher level, so this is a hierarchical process. The robot learns first which graph vertices to plan to, and between two graph vertices actually we use a local policy trained on with reinforcement learning, in which takes the visual input as guidance. So this works actually pretty well. Next thing is temporal attention. So while the first two maps here are classically used in robotics for a long time, the next two actually are really machine learning contributions, and in particular temporal attention, which obviously, as you probably know, dominates machine learning in practically every field we can imagine right now. And this also has been used for navigation. I will not go into details. So this is my only slide. There is lots of work, recent work. Cordelia also has work on that, the episodic transformer. So how does this work? Basically, these models break the Markovian assumption in decision taking, and instead of taking the decision based on some memory which we maintain, they actually make it possible to attend over either the full history of observations or at least a very, very long horizon of that. And that can improve performance a lot. I will not go more into details here, because I will actually spend the remainder of this talk to work we have proposed recently, which are implicit representations for navigation. So what are implicit representations? You heard about nerves probably. I actually found it quite difficult to define what an implicit presentation is, and I found two different definitions. First, through the implicit function theorem, which is used when you have some function of interest, phi here, and you don't have an easy means to explicitly specify it, but you can do it by proposing a second function f, and the level set of this function here corresponds to the function which really interests you. That's one way of seeing implicit representations. The second one is an implicit representation is basically a representation of some geometric object, a shape or a scene or something like that. And instead of defining the shape explicitly through some discretized representation like meshes or voxels, you can actually learn parameterized neural networks which map coordinates through some quantities of interest like density, occupancy, signed distance. There's even an overlap here because if your function f here is a signed distance field, then this f here corresponds to this, and the level set of the signed distance field would then be the surface of your scene. So how are these things used in robotics? Well, in various ways. For example, here we have representations, they're always representations of the scene. For example, here we have an implicit representation of the signed distance to a target. This means that navigation is basically gradient descent. You can do gradient descent on the representation. Here, model predictive control is augmented with an implicit representation which lets you avoid occupancy. But in this kind of work, I don't know how the other speakers did it, but I'm really troubled here. So I honestly push the right buttons, but they're correlated. My fingers are too big, I guess. Yes. Okay, something is happening here. Yes. So these two line of works actually require that the representation has been created before the episode. They are not dynamically created, so you need to first reconstruct the scene and then you navigate. Then there is recent work, for example, this work here by Andrew Davidson's group, where the representations here, nerves, are actually generated dynamically. So as the robot navigates through the scene, it generates the representation. But on the other hand, the representation is not used for the navigation process itself. So there is no downstream task on navigation which uses the representation. So in our group, actually, we would like to tackle that, and what we proposed is exactly this. So we proposed two different types of implicit representations. So this is work of my student Pierre in collaboration with colleagues from INSA Lyon. And so these are 2D implicit representations, and they are dynamically created. So at each robot step, at each step of the agent, we need to update a map, and the map is a neural network. So we need to do backpropagation and learning even after training the robot. After training is deployed, learning is done at each step. And this is a lifelong learning problem, since if you do that, then what you learn at the beginning of the scene must not be forgotten at the end of the scene, which can be done if you just naively train your neural network. So we have two different representations here. The first one is a semantic finder, which actually directly maps semantic embeddings to positions, and this allows to store where key objects are, for example, where are things I might search, but which is not so helpful in finding out where occupancy is and how can I actually avoid obstacles. So we have a second one, and the second representation is a coordinate network, like a nerve. So it maps coordinates directly to information of the scene. In this case, 3 classes: unexplored, navigable, or occupied. And so both of these are input to an agent, which updates them and uses them on the fly. So the problem with the second one here is that we probably need some global reader on that, because as we put coordinates into the network, planning would require that I iteratively actually query it, say, can I go here, can I go here, can I go here? And if I just want to solve something like an A-star algorithm, then it would result in a large amount of queries here, which is obviously not tractable. So what we proposed here is a global read which directly maps from the function space, because this is a function here, maps from function space directly to some embedding space from which I actually can navigate. So that's exactly what we did. We have this global reader, and the function space is represented by the neural network weights itself. So we train a second neural network, which is trained once for all, not dynamically. We train a second network, a global reader, which maps from the neural networks of the implicit representation directly to a usable embedding. I will not go into details. This raises a couple of questions. For example, a desired property we would like to have is invariance. If I have two different representations which are the same function, then we would like to have the same embedding. The problem is this representation is implicit. It's an MLP. And if I take one MLP, I'll take two hidden units of this MLP and I permutate them. I maintain the same function, but it's different weight matrices, right? So we don't have this invariance property which we require. And we couldn't solve this exactly, but we go into this direction using a transformer-based solution. I will not have the time to talk about that. So I'll finish up by just showing how this actually works. This is the same recurrent baseline I have showed before. So I still have this recurrent memory here. We have the same inputs. And what we just do is we add these two implicit representations here. So the first one is connected to the query, the target we need. And the second one basically means the global reader here just is input to, the output of the global reader is input to the agent. Now, of course, we need to fill these guys. So what we do is we use a replay buffer during training. Training means during each agent update, and this replay buffer is filled from observations. So we have the visual observation here, we do some pre-processing here. This fills a replay buffer, and the replay buffer, from the replay buffer we sample batches and update at each agent step we update the implicit representations. This works quite well. I'll finish with results. So this is work which is currently under review. We'll get the review, hopefully the answer tomorrow. And we obtain new state-of-art results on multi-object navigation with this technique. I'll wrap up here. So as a conclusion, we are interested in creating robots which are situation aware, which are capable of high-level reasoning, and we put a strong focus on sim-to-real performance, so performance in real environments. And to that end, we combine machine learning, computer vision, geometry. This requires large-scale training, finding the proper inductive biases. So how can we organize memory in robots in the most efficient way? Thank you very much. I'm happy to take questions.
Thank you for the nice talk. I think we have time for one question. We have some questions in the room.
I have a clarification question. So, your reader needs to be reading a neural network representation so that it better generalizes. You get into the situation where you might need the key, and then the F. I mean, what you have as the F that is read by the reader. That needs, what is exactly the advantage of the F being the implicit representation that is the neural network and not, say, a classical map where, your keys are and something that is more transparent? Does that more transparent, more traditional thing generalize worse, or why do you need the implicit representation there when you still have the reader afterwards?
Okay, that's an excellent question, and it's true that I didn't actually talk about it, and I should have. So. There are a couple of advantages of the implicit representation. First of all, it has a fixed budget, and it can, if you have a tensor, a metric tensor, then basically current metric tensor is limited to 32, 48, 50 values, at least in the neural ones, right? If you run ROS on your robot, you can have maps which are very, very large. But if you use them as inductive Bayesian neural network, you can't do that for lots of reasons. Just the amount of memory which needs to pass through is just not possible. So these maps are very small, and which means basically when the robot moves out of its history window, it has forgotten what it had seen before. So here you're in a fixed budget, and basically the network itself adapts to to its amount of information it has seen. The second thing is neural networks are pretty good at interpolation, and we exploit this here. So if you haven't seen something in a metric map, then there are holes, right? And if there are holes in there, then the planner will just fail. Whereas here, through the fact that it's a neural network and it interpolates, hopefully, and that's what we a little bit checked in the paper, you can use this through interpolate through, right? So.
Thank you. Thank you for the answer.